Hello, Chem students. I'm going to go over some Chapter 1 material. There'll be a few other videos on Chapter 1 coming up. But on this one, I'm going to look at atoms, Zeffective, ionization potential, atomic trends, polarity. Okay, so these are all important ideas that you want to get down pretty well right at the start. So we'll begin. Our main atoms that we're going to talk about in organic chemistry are carbon, hydrogen, oxygen, and nitrogen. These are also the main atoms of biochemistry, which a lot of you guys will have to take too. Biochemistry will probably be more important in the coming decades due to medical reasons, pharmaceutical reasons, and things like that. We're also going to look at some of the halogens, partly for trends and partly because of chemical reactions that we study. So fluorine, chlorine, bromine, and iodine. The main one we're going to look at later on is bromine. And some of the atoms that are important in biochemistry are related to the ones we study up here. If you come down here and look at the periodic table, you'll see in the same family as oxygen you find sulfur. So sulfur is a really important atom in biochemistry. We'll talk about it a tiny little bit later in the course. Of course, phosphorus is a super important one because of all the phosphates, ATP, ADP, all the phosphorylated proteins and stuff like that. But that won't be so much important to us. We will have one reaction called the Wittig reaction later on. Some of the metals, they're just counter ions. Sodium is a plus, potassium is a plus, lithium is a plus, and they counter a negative charge. Boron and aluminum, we'll talk about those a little bit later on. Chromium will be real important after, I think it's chapter 10. Then chromium will become very important. And we'll have a little bit on copper perhaps. Okay? So I have those down here in the periodic table. You can take a look at where these are. But our main atoms are going to be these guys right here. We want to know a little bit about the atom. So the atom is a very simple little model that we have. We have a nucleus. The nucleus, it turns out, is very, very tiny. Okay, if you compare the radius of the atom to the radius of the nucleus is only 1/100,000th the size. So it's incredibly tiny. On the other hand, the mass of the particles in the nucleus are very, very big compared to the electrons that are in the cloud around the nucleus. So if we come down here and look at the mass of a proton is about 1,800 times more than the mass of an electron. But as far as the size goes, the nucleus is extremely tiny. So we're going to have two kinds of electrons around an atom. We have the electrons in full shells. Okay, these are full shells and subshells. These are called core electrons. They're held very tightly by the atom, and they're not involved in bonding. Okay, and then we have the electrons on the very outermost, which you should remember from your freshman chemistry. These are called valence electrons, and these are extremely important in terms of bonding patterns. They decide how many bonds they have, how many lone pairs they have, and things like that. If we look at the nucleus a little bit in more detail, there's protons in there, and the protons decide what kind of element it is. For one proton, that would be hydrogen. For 6 protons, that would be carbon. For 7 protons, that would be nitrogen. For 8 protons, that would be oxygen. So the proton kind of defines the element. If you look at the number of neutrons in there, they define the isotope, which we're not going to spend a lot of time on isotopes, but you know, they will be important a little bit. In Chapter 9, we'll talk about different types of isotopes. Okay, atomic configuration, you might remember from freshman chemistry, has to do with the 1s, the 2s, the 2p, the 3s, the 3p, and so forth. I have some of those on the next page. We'll take a look at that. Okay, it just shows how many orbitals are involved and how many electrons in each orbital. Now, when we talk about atomic configuration, it's not going to be the same as talking about an atom and a molecule. Atoms and molecules, they have kind of different properties, but we're going to start off with atoms alone so that we can understand some of their individual properties. We have the core electrons, which I already mentioned. Those are in full shells or subshells, completely full. And then the valence electrons in the outermost layer, shell. And these are always trying to be like the noble gases. Okay, the guys over on the very, very far right. That would be the helium, the neon, the argon, those guys. Okay, so a picture of an atom as you might see in freshman chemistry, you'd have the nucleus down here. Z represents the number of protons, so that's going to define the element. And then we have the 1 shell, which only has the 1s. Then we have the 2 shell, which has the 2s and the 2p. If we were to keep going, we would add another subshell called the 3ds. And each time we go up, there's 2 more of the next type of orbital. So there's only 1 s orbital. But then when I go to the 2p, there's 3 p orbitals, px, py, pz. And when I go to the d, there's 5 d orbitals. And each of those orbitals can hold 2 electrons. Okay, so there's some rules that are followed to fill up those electrons, but I'm just going to tell you, you probably saw these in freshman chem. This won't actually be something that we stress in here. But the off-bound principle is just sort of logic. We just fill up the electrons from the lowest energy levels towards the highest, okay? Because it's easiest to put the electrons that are held the tightest in the lowest energy orbitals. And so it's just like, say, filling up a glass of water. You don't fill up the top of the glass until you fill up the bottom and the middle of the glass. Hund's rule says that when you put electrons into subshells that have more than 1 orbital, well, that's not the s orbital, but that would be the p orbital. So if you look at the p's here, there's 3 of them. And it says when you put in 1 electron, it goes into a 2p. But when you put in the second one, it goes into a different 2p. And when you put in a third one, it goes into a different 2p. And that's because the electrons all repel each other. They don't really want to be together because they all have the same charge. But when you come to the 4th electron, you have to start pairing them up. Okay? So then you fill it in. Now when you pair them up, they have opposite spin. So generally we just write an arrow up and an arrow down to mean that they have the opposite spin. And that's full. Now you can't put any more electrons in there. So that means the total number of electrons you could fit into the 2 shell would be 8. 2 in the 2s and 2 in each of the 2 p's, and that would add up to 8. So they call that the octet rule. That rule applies to a lot of atoms in the 3, using the 3 shell, but not all, because we have these d orbitals out here. So the octet rule is always true of the 2 shell, and that's going to be mainly our shell that we look at, because carbon's there, nitrogen is there, oxygen is there, fluorine is there. Okay, hydrogen only uses the 1s, so that does not have an octet rule. That has what they call a duet rule. Okay, so we said, what I just said was that everybody tries to be like these guys over here. These are the noble gases, or the inert gases: helium, neon, argon, krypton, xenon, if we kept going. And so they all want to be like this. So if you're just to the left of neon, what you need, fluorine needs 1 more electron. Oxygen needs 2 more electrons. Nitrogen needs 3 more electrons. And so that, in fact, is going to determine the number of bonds that they make, because they're going to get those extra electrons by making bonds. If you go the other direction, say if you go over here, sodium has 1 electron too many to be neon. So sodium loves to give that electron away, and the only way we find sodium in our world is a sodium +1. We can make sodium metal, but that's man-made by forcing electrons back onto the sodium atom. And it's very reactive. You may have seen it tossed into water and catch on fire. Magnesium has 2 electrons too many, so it can lose 2 electrons to be like neon, and that's what it does. So if you look at magnesium in nature, it's always +2. Again, we could make magnesium metal, but we have to force the electrons back onto the metal, and it's very reactive. But we'll look at this later, because we're going to make something called Grignard reagents, and they use magnesium metal. And that would be true, say if I'm looking at helium right here, hydrogen would want to get 1 more electron, and that's what it does. It does that by making a bond. And lithium would want to give away 1 electron, become a lithium +1, and that's what it does. Okay, so we could write atomic configurations of these guys, and say the hydrogen -1 is going to look like helium, the lithium +1, the beryllium +2, they're all going to look like a 1s2. The neon, each of these guys would pick up extra electrons, 1 electron or 2 electrons or 3 electrons, and each of these guys would lose electrons, 1 electron, 2 electrons, 3 electrons, but they would all have the same atomic configuration, okay? Because that is a completely filled 2 shell, and that is the ideal goal of all the atoms around neon. Okay, and that would be true if we went up to argon all the atoms around argon as well. Okay. Also, as you go up in number of orbitals, so n equals 1, n equals 2, n equals 3, you're actually pulling that negative charge farther and farther away from the positive nucleus. And that's going to make these electrons have greater and greater potential energy. Okay, it's like stretching out a rubber band, you could think of. You're just pulling it out farther and farther and farther. Okay. Now this is going to be something very important. We'll be talking about this all the time, or I'll be talking about it all the time. This is called something Zeffective. Okay, so Zeffective is going to be the positive charge that the valence electrons feel. Okay, and that's going to come from the total charge, Ztotal. Remember, that defines the element. So if this was carbon, that would be +6. Minus the core electrons. And those are the electrons in the completely full shells or subshells. Okay, because these are going to block the valence electrons from the Ztotal that has that positive charge. So let's take a look at hydrogen. Hydrogen is +1 Ztotal. There are no core electrons. So any electrons in a bond around a hydrogen are going to feel the full effect of that +1 nucleus. If we go over to helium, it has the +2, and there would be 2 electrons. They would feel a +2 instead of what hydrogen feels, a +1 over here. So you can imagine that the helium electrons are going to be held much more tightly than the hydrogen electrons, because they have twice the positive charge holding those electrons to the nucleus. Now if we come down and look at the second row, the n equals 2 shell, Ztotal keeps going up. Remember, +3 defines lithium, +4 defines beryllium, +5 defines boron, +6 defines carbon, and so forth across the row. Now every one of these guys has a completely full n equals 1 shell up here. Okay, that's how we got here. So for every one of these guys, the valence electrons, which are in the n equals 2 shell, are going to be shielded by the -2 of the n equals 1 shell. And so to see what that valence electron feels, we're going to have to subtract a -2 from whatever the Ztotal is. And that's going to be what we call Zeffective. So for lithium, it only has a +3, -2. The Zeffective would be +1. For beryllium, it has a +4, -2. The Zeffective would be +2. If we come over and look at carbon, carbon has a Ztotal of +6, -2. It would have a Zeffective of +4. And nitrogen would be +5, and oxygen would be +6, and fluorine would be +7. And finally, at the perfect row right here, the noble gas, we have a +10 in the nucleus, the total, -2, so it feels a +8. So now if you think about it, the electrons in the valence shell out on the outermost shell are going to feel a larger and stronger pull as we move to the right. So the valence electrons on neon feel a +8 holding them to the atom. So they're going to be held a lot tighter. And that's going to be true on every row as you go across in a horizontal direction. Okay, Zeffective always goes up and it's canceled out. If we look at sodium, it would have a completely full 1 shell and a completely full 2 shell. That adds up to 10 electrons. So I'm going to take away a -10 from whatever its Ztotal is, which is +11. And that leaves a net of +1. So in fact, if you look at the second row and the third row, the first column has a +1 and a +1, and even down to potassium, a +1. In the second column, it's all +2. In the third column, it's all +3. So as we go across horizontally, the electrons in the valence shell are held tighter and tighter and tighter. Okay? Now the other direction is to go up and down. So if we go up and down, what you see is that the +1 here, the valence electrons that are feeling that +1 are right at the +1. So they're going to feel it the strongest. If I look at lithium, I have to pull the valence shell out a little bit. I'm in the n equals 2 shell. I still have a +1, but the valence electrons are farther away. So they're not held as tightly. And if I go to the sodium, I'm now in the n equals 3 shell. Then that valence electron out of the n equals 3 shell is not held as tightly as the lithium. And if I go to potassium, it's not held as tightly as the sodium. So the electrons are held tighter when you go up towards the top, and the electrons are held tighter as you go across horizontally. And you want to have a good idea about why this is the case. Okay? So if we're looking at a list of choices here, what atom holds electrons tighter? Would it be H or helium? Oh, let's just look at those two. H is here, helium's over here. They're in the same row, and helium has a +2, so helium's going to be higher than hydrogen. Okay. Now, would it be potassium or these guys? Well, if you look at potassium, it has a +1 just like hydrogen, but its valence electron is way farther away. So it's going to be less than hydrogen, which is less than helium. If we look at krypton, where's krypton? Way over here. It's an inert gas, a noble gas, and it's way down here. So krypton has the same Zeffective, actually not exactly the same, because this is a +8 and this is a +2. So that's kind of a hard one to choose between, because it looks like krypton has a bigger Zeffective, but the effect of the +2 right next, the electron right next to the +2 is the greatest. So it turns out that helium has the strongest pull on electrons in the whole periodic table. Which electrons are held looser? Okay, well, it's going to be the ones that are towards the bottom and the ones that are towards the left. So if we look at all these choices, the one that is most towards the bottom and most towards the left is the potassium right here. So the potassium would lose its electron very, very easily. Okay, in fact, it's quite reactive. If you tried to work with it and there's any moistures around, it could catch on fire real easily. So the periodic table kind of tells you what the atomic configuration should be. This isn't like super important to our course, but you should have sort of an idea about how the periodic table is constructed. Okay, so if we look at the first two columns, these are the s electrons. Up at the top, the 1s, the 2s, the 3s, the 4s, the 5s, the 6s, 7s. If you jump across here, of course, helium is still in the one shell, that's 1s. But if you look at the second row, now we're into 2p. So there are going to be 6 elements here. Okay, so that would be the boron, the carbon, the nitrogen, the oxygen, the fluorine, and the neon. Okay, those would be the 6 guys. And then that's full, so we have to jump over to the 3s. And then we start the 3p. Now, this is where the periodic table tells you the answer. You think, well, maybe 3d would come next. But what the periodic table shows you is the 4s fills in first, and then the 3d, and then the 4p, and then the 5s fills in before the 4d, and then the 5p, and so forth. Now, you might have done something like this in freshman chemistry, where you wrote out each row, and then you drew arrows through them. This is going to tell you the same thing that the periodic tells you up here. So you might take a look at that and see if you can figure it out. Now remember, as far as Zeffective goes, we know right where the strongest pull on the electrons should be. It should be towards the top, and it should be towards the right. So the strongest pull on electrons are going to be up here in this top right corner. In an opposite sense, the electrons that are held the weakest, the loosest, will be towards the bottom and towards the left. So elements that are down here will have a very weak hold on their valence electrons. Now there's actually an experimental reaction that we could look at that will tell us if this is true or not. It's called ionization potential. So what we do is we steal an electron away from an atom. That's going to take energy because the nucleus has a positive charge and the electron has a negative charge, and that's why they're attracted to each other. But we can come in and put in a lot of energy and pull that electron away. And if we do, we can measure the amount of energy that it took to do that. And so that should give us a quantitative number that we can use to test our ideas about how strongly electrons are held. Okay, so now we have a little potential energy diagram here. The way chemists and I guess physicists represent energy, certainly chemists do this, they have a lower level that is more stable. Okay, that has less potential energy. And then as you go up, you have higher energy, higher potential energy, and it's more reactive. So things that have less potential energy are more stable. Things that have higher potential energy they can be more reactive. So what we're saying here is it's going to cost us energy. So we're going to have to go up in energy. That'll be a plus value. So greater potential energy is less stable. It's going to be a plus number relative to our starting point. So whatever this difference is, that'll tell us how hard was it to get that electron away. So let's take a look. We're thinking as we go across from hydrogen, it's going to be harder. Well, first off, look at this is a huge number. You may not have an idea about this because, what is a kcal? So kcal is actually, just to give you a little feel, kcal is like 1 food calorie. So in that sense, it's kind of small. But in terms of atoms, this is a big number. Okay, 314 kilocalories. Now I'm thinking helium's going to hold it tighter. So I go all the way across and I see 568. It is way tighter. Okay, so you can sort of look at, this is the one way I look at it, is that a kcal is 1,000 calories. And so you could sort of think as a kcal is like $1,000. So if I have a difference of 1 kcal, say I have 314 and 315, that would be like $1,000 more to do whatever that process is. But in this case, it's not 1,000 more. It's not 1 difference. This is, what is it, 254,000 different. Okay, so we'd say $254,000 different. Or you could also look at it as you got to climb a hill that's 1,000 feet for 1,000 calories. That's going to be a lot of work. That would be like climbing a hill here that's 254,000 feet tall. Not even possible in our world. Now, if we go down, we're thinking that lithium's not going to hold its electron as tight because it's farther away, and they both have a Z-effective of +1. And sure enough, that's the way it is. And then if we go to sodium, it's even less. If we go to potassium, it's even less. Because that 1 electron in that outer shell, that valence shell, is getting farther and farther away, and the Z-effective is always +1. If we come over here, let's look at carbon. So the next one down from carbon would be silicon. You can see it doesn't hold its valence electrons as tightly as carbon does. Okay, and if we come all the way to fluorine, we can see fluorine holds its valence electrons way tighter than carbon. And in this row, the one that holds it the tightest would be neon, but not as tight as helium. Okay, now there's actually a couple places where it kind of is not exactly the way that I'm telling you. You might have seen this in freshman chemistry, I'm not sure. But when I go from beryllium to boron, something happened there that's a little different. I went to a different shell. So here would be beryllium with just 2 electrons, but then when I go to boron, I have this extra electron that's in the higher shell. So this is a little bit easier to pull this electron away than the 2s shell. Okay, and so when we come up here and look at this, beryllium's 215, we're thinking boron should be higher, but it's not. It's a little bit lower. So I'm not going to hold you to this. I'm just letting you see where there's this exception. But as soon as we go from boron to carbon, it starts jumping back up again, and then nitrogen jumps up again. Then we have one other place where it's a little bit not as predicted. Okay, so when I go from nitrogen to oxygen, look what happened. It fell. So what's happening there? Well, nitrogen has exactly half full 2p shell. That's actually a very comfortable arrangement for the atom. Kind of like when you have the full shell full of electrons, it's kind of a minor stability. But now when I go to oxygen, I have to put another electron in here. So now these two guys are repelling each other. That's going to cost us a little energy to put it in there, right? So this orbital has more electron repulsion. And so it's easier to take that electron out. And that's what we're seeing here. It falls off. But then it starts right back up again. Okay, so there's these 2 exception areas. If you look at this, the 5th row going to the 6th row, and if you look at the second column going to the 3rd column, and 5th column going to the 6th column, they don't exactly follow what we were saying according to Zeffective. But we have other properties where it works perfectly. Okay, so let's first take a look at this example here. Which atom has the highest ionization potential? So we got these choices: sodium, silicon, chlorine. It turns out they're all in the same row. So we really should know this because sodium has a Z-effective at +1, and silicon has a Z-effective at +4, and chlorine has a Z-effective at +7, and they're all in the same row. So we know chlorine's going to have the highest ionization potential. Hardest to pull electron away from here. Greatest electron attracting power. Okay, this is going to be real important when we start making bonds. And here's the numbers right here. So what if we look in a column? Okay, these are all halogens: fluorine, chlorine, bromine. So we're thinking, well, they all have a Z-effective of +7, but the electrons in the valence shell are closest to the fluorine. Okay, so they're going to have the highest ionization potential. And it should be down here. The lowest ionization potential should be on bromine. Chlorine will be in the middle. And so what did I ask here? I asked here what has the lowest ionization potential, trying to be tricky. Okay, up here I said the highest, now I'm saying the lowest. So the lowest should be the bromine. It should have the smallest number. Let's see what we got. And so that is the case. Okay, but you should be able to answer it either way, highest or lowest. Now what if I look at it like this? What if I compare oxygen to chlorine? This is actually a pretty hard comparison, because our rule is it's higher to the right, but it's also higher the farther you go up in the table. So we have something saying oxygen should be higher, and we have something saying chlorine should be higher. Okay, well, let's look at the data and see what happens. Looks like the oxygen won. So the oxygen is a little higher, and so we say, oh, well, maybe that's going to be the case. Okay, so if it's higher up, even though this is more to the right, maybe that's the way it's going to be. Well, let's take a look at another example. Okay, so here's oxygen. Whoops, I made a boo-boo. That should be sulfur versus bromine. Which of those has a higher ionization potential? So if we follow our example over here, we'd say, oh, well, oxygen did. Okay, so that should have the bigger number over bromine. Okay, let's see. We were wrong. So bromine is farther to the right. That means it should have a higher number. But sulfur is higher up in the table. That means it should have a higher number. So you can see in this case, this is an ambiguous case. We have some examples where higher up is better. We have some examples where further to the right is better. Okay, so this might be a good freshman chemistry question, but that's not going to be the emphasis of our course. We just want to know the basic, obvious trends. Now this one's going to be obvious. And again, I messed up the atoms here. I should be comparing sulfur to fluorine. That's what happens when you copy and paste. So this one should be easy, because fluorine's further to the right, so it should have the higher ionization potential. And fluorine is higher up in the table, so it should have the highest ionization potential. So fluorine should have the highest ionization potential. Okay, let's see if that's right. And it is much higher, 402. So when you look at a periodic table, everything's pointing towards the fluorine direction. And you might remember from freshman chemistry that fluorine was the most electronegative atom. Okay, let's take a look at sizes of atoms, sizes of cations, sizes of anions. These all follow the Zeffective rule, very straightforward, there's no exceptions. Okay, first off, we're using these funny little units, picometers. Pico is 10 to the minus 12. When I was a student, we used angstroms because they just noticed it's a 1. I didn't have to think about 10 to the minus anything. I didn't have to think about 100. But that's okay. Nowadays, they use picometers, and so 100's kind of like 1 angstrom when I was a student. That's kind of like the normal bond length in the range of 100. Okay, or the normal atom size in the range of 100 picometers. So if we look at this right here, we have n equals 1 shell. This is the tiniest that you can get. Okay, there's only 1 shell. And here I have a plus 1 holding onto those electrons. And if I go all the way across, I have a plus 2. And just as you would expect, if I put a plus 2 there, it's going to pull those electrons in way tighter. So that's a Zeffective argument. Okay, you want to be very familiar with this. We have many examples here that I'm showing you. Now, if we go across the second row, this is the row we're really interested in because we have carbon and nitrogen and oxygen and fluorine. We start off kind of big. Now, note, we went up a whole shell. So this is the 1 shell. This is the 2 shell. Well, you got 2 shells. It's farther out there. Okay, it's like the second layer on an onion, and then the third layer, and the fourth layer, and the fifth layer. It keeps getting bigger and bigger and bigger. Okay, so the lithium's at 167. Now we're thinking if we go from a plus 1 to a plus 2, it should get smaller, and sure enough, it does. If we go from a plus 2 to a plus 3, it should get smaller, because remember, the electrons are negative, and the nucleus is positive. And this is a positive 3 instead of a positive 2. If I go to carbon, it's a positive 4, and it gets smaller. If I go to nitrogen, it's a positive 5, and it gets smaller. If I go to oxygen, it's a positive 6, and it gets smaller. And if I go to fluorine, it's a positive 7, and it gets smaller. And if I go to neon, it's a positive 8, and it gets smaller. Okay, so that's going to be the case in every single row. Now, if we go up and down a column, each time we go to the next row, it's an extra layer of electrons. So, say helium going to neon, it gets bigger. Neon going to argon, it gets bigger. Argon going to krypton, it gets bigger. krypton going to xenon gets bigger because we have a whole extra shell of electrons, whole extra layer. Okay, so those are two ideas there. Okay, there's the Zeffective, which holds tighter and tighter and tighter as you go across, and then there's the size of the atom according to the number of shells of electrons. Now, if I start up here, say I have a lithium atom. Remember, it's got that one extra 3s electron. I'm sorry, 2s electron. And so if I take that away, I lost the whole shell. Okay, it just got a whole lot smaller. So now I have the n equals 1 shell. I have 1s2. And the lithium's plus 1, so I have less, fewer electrons repelling each other. And I have a plus 3 down here holding on to the 2 electrons that are remaining. And notice it went from 167 picometers to a 90. It really contracted because now we only have the n equals 1 shell. Now if I go from lithium, which is plus 1, to beryllium, which is plus 2, I'm thinking now, remember beryllium has a plus 4 nucleus. And these 2 electrons that are remaining are going to see that. I've gone way down from 90 to 59. And if I could go over to boron plus 3, it would contract even more because they're going to be held even tighter. Okay, because boron has a plus 5 nucleus, 41. Carbon doesn't really do this. We can't really make a carbon plus 4. So you'll notice I don't have anything in the middle here because carbon likes to make bonds, covalent bonds. It doesn't like to be a cation. It doesn't like to be an anion. It just wants to have things bonded to it. Okay. Now again, as I go down a column in the periodic table, I get more and more layers, and so it gets bigger and bigger. But if I compare any one, say sodium right here to sodium up here, this is way smaller because we don't have that one valence electron there. Okay. Now if I come over and look on the other side, I'm doing exactly the opposite. Here I'm taking electrons away from the atoms up here. But remember, nitrogen, oxygen, and fluorine, they want to be like a neon, have 10 electrons. Well, fluorine would need to pick up 1 electron. But if I have an extra electron, I got more electron repulsion, so it should actually expand, should become bigger. If I come up and look at fluorine up here, without that extra electron, it's 42 picometers. But now I put an extra electron in there, woo, it really puffs out to 119. Now if I look at oxygen, 1 electron isn't going to do it. To get to neon, I need to get 2 electrons, so we can have oxygen minus 2, say in barium oxide, some salt. But now I got 2 extra electrons, so they should repel each other even more than this 1 extra electron, so it should be even bigger. And look at that. Sure enough, it is. Also, the Zeffective on fluorine is plus 7. The Zeffective on oxygen is plus 6. Who's going to hold on to the electrons tighter? It's going to be the fluorine, with only 1 extra electron. And then if I go to nitrogen, which can actually have N minus 3, nitride, I got 3 extra electrons, and the Zeffective now is only plus 5, so this should puff up the most. This should be the biggest, and it is. Okay? Again, if I add an extra layer, it gets bigger and bigger and bigger. So you should be able to look at these tables and explain these trends, these directions that things are going. Okay? That's a common question that I might ask on an exam. Explain the atomic distances, say in the second row. Well, this would be the Zeffective. Okay, these are all atoms, and the Zeffective of neon is plus 8. So it's really pulling in those electrons tightly. Whereas the Zeffective of lithium is only plus 1. Explain the cation distances, lithium, beryllium, boron. Okay, so all of the cations are smaller than their atoms, well, because I lost that valence electron, those valence electrons. These all only have 2 core electrons left. The n equals 1 shell, 2 electrons. But as I go across, lithium is plus 3, Zeffective, beryllium is plus 4, boron is plus 5. Okay? And then if we look at anions, we just explained that up there, remember. Nitrogen has 3 extra electrons and a plus 5 Zeffective. Oxygen has 2 extra electrons and a plus 6 Zeffective. So there's less electron repulsion and there's a greater Zeffective. And then fluorine would have a plus 7 and only 1 extra electron. So that should be the smallest. Okay, we're going to be looking at bonds coming up here pretty soon because we're not going to always be talking about atoms. We're mainly talking about molecules. We're going to have 2 types of bonds, 2 types of covalent bonds. Just to remind you, covalent means they're shared. They can be shared evenly, so pure covalent, or they can be shared unevenly, polar covalent. But we'll talk about that soon. So sigma bond means all the electron densities directly between the two bonded atoms. So we're going to have like atom A and atom B. Atom A could be carbon, nitrogen, oxygen, or some halogen. And atom B could be the same thing, carbon, nitrogen, oxygen, or halogen. Okay, and they share the electrons directly between. That's a sigma bond. Sigma bonds are always the first bond. If there's only one bond, it will be a sigma bond directly between the two atoms. Now, the other thing that we have in organic chemistry is we have bonds to hydrogen. Okay, CH bond, NH bond, OH bond. So these are going to be very important. So this is also a sigma bond because the hydrogen can only make one bond. So it has to be sigma. So these are the atoms we're going to be working with. You can see them right there. We could also have what we call double bonds or triple bonds. So a double bond means there's a second bond between the atoms, and we can't do that with a sigma bond. A second bond is always going to be what we call a pi bond, and a third bond is always going to be a pi bond. And the pi bonds will be made between p orbitals. So for us, it'll be two p orbitals. Okay, and that'll be that's a second bond or third bond. The pi density could be above and below, not in between, or it could be in front and in back, not in between. Okay, so those will be pi bonds, and we're going to have to draw three-dimensional structures, coming up pretty soon. So when we look at atoms, they're going to be very different as an isolated atom versus in a molecule. Okay, so our goal is actually to understand the atoms and molecules, and that's going to involve sigma bonds and pi bonds. We'll also have to worry about how tightly the electrons are held. So the electrons could be between two equal atoms shared very evenly, or it could be one atom has a greater attraction for the electrons. Remember, we just looked at that, Zeffective, and how close is it to the nucleus. So things that like to attract electrons to themselves more strongly will be more partial negative. And we could get so extreme that the electrons are totally stolen away, and then we would have something that we call ionic. So that'll be our chapter 2. We're going to talk about polarities and types of bonding and so forth. That'll be coming up. Okay. So we're going to have something we call electronegativity. You probably remember that from freshman chemistry. Electronegativity measures the attraction an atom has for electrons in chemical bonds. Okay, so you have to make a chemical bond to be talking about this. And so you'll notice over here that we don't really talk about electronegativity with helium and neon and argon because they don't really make chemical bonds. So in the periodic table, the atom that has the strongest hold for electrons is going to be fluorine up here in the upper right corner. So there's all kinds of different electronegativity scales, but the one we're going to use is related to what I just talked to you about in terms of ionization potential, the Pauling scale. And so there's numbers. They go really from a pretty low number, say something like 0.8 to about 4 for fluorine. They'll be in between those two extremes. So hydrogen is about in the middle, 2.2. And then we would expect helium to be much stronger, but helium doesn't make bonds, so there's no number. Now, if we come back over and start at lithium, we know it doesn't hold its electrons very tightly, so it's a low number. If we go down, it should be even a lower number. If we went down, it should be even a lower number, because remember, they're getting farther away from the nucleus. So they're all pretty close to each other, but it is a little bit of what I just said. They get a little bit lower. As I go across, I'm thinking the electronegativity should get bigger because the attraction for the electrons should get bigger because the Zeffective is getting bigger. So beryllium has a +2 and the electronegativity went up. Boron has a +3 Zeffective and electronegativity went up. Carbon has a +4, the electronegativity went up. Nitrogen +5, it went up. Oxygen +6, it went up. And here we are at fluorine +7, that's the highest, and it went up. So this is our highest electronegativity. If we look up and down, you can see the chlorine's a little lower because it's farther away. If I look at the bromine, it's a little lower because it's farther away, and the iodine's a little lower because it's farther away. But they all have a +7 Zeffective. Oxygen and sulfur follows the same pattern. Nitrogen and phosphorus, same pattern. You can look across here and see the pattern. Now, if we want to calculate how polar is the bond, polar has to do with charge separation. So we're going to have a partial minus and a partial plus, or we'll have a full-blown positive and negative charge, like ionic salts. Okay, so we have to look at the two atoms, A and B, whatever they are from up here in the periodic table. They'll have electronegativities. So we're going to look at the delta between them. And we don't care if it's positive or negative. We're going to just take the absolute value. So I have the electronegativity of A minus the electronegativity of B. So basically it's a delta, it's a difference. Now, if that difference is less than or equal to 0.4, we're going to consider that bond to be a pure covalent bond and that the electrons are shared evenly. Okay, let's take a look at something like hydrogen, 2.2, and carbon, 2.5. That's only 0.3. So if we look at carbon-hydrogen bond, we're going to consider that's a pure covalent bond, no polarity in that. Now, if it's more than 0.4, the difference, but less than, and the book I used actually used 2 as the number, but in reality there's a whole wide range here of ambiguity. They're going to say this is a polar covalent. So there's still a bond, they're held together, but there's a charge separation, so it's a partial positive and a partial negative. Okay, so I put here 1.4 to 2 because there's a range. Excuse me. It's not always 2. There's many exceptions. And then the book that I got this out of, they said if it's over 2, then it's ionic, and that's probably true. But I put if it's over 1.4 to 2, because there's some ionic things that have less difference in electronegativity than 2, but clearly they're ionic and not covalent. So there's some ambiguity here. We'll be able to easily tell if it's ionic or covalent because ionic substances have very, very high melting points and boiling points, whereas covalent substances tend to have much lower boiling points and melting points. So let's take a look. All right, I put in the ones in blue here, the guys that we should be sort of familiar with. You should almost memorize these guys. I'm not going to hold you to memorizing them, but it would really help you if your thinking was very clear on what these numbers are, because this is the electron attracting power for these atoms and bonds, and that's what you want to know. Okay, so let's take a look at an example. So I have here a structure, and I'm pointing at 3 bonds. I'm pointing at a CH bond, I'm pointing at a CO bond, and I'm pointing at a sodium bond right here. So we want to know, is this ionic, is it polar covalent, or is it pure covalent? Okay, when we come up to the periodic table, we already did it. H and C has a difference of 0.3. So we would say that's pure covalent. So what about carbon and oxygen? So carbon is 2.5, oxygen is 3.5. So the difference would be 1.0, and 1.0 is less than 1.4. So this is going to be polar. Okay, so there's a separation of charge, but not complete. It's not ionic. Now, you should be able to know and guess which end is going to be negative. Because oxygen has greater electronegativity, it's going to be the negative end, and the carbon is going to be the positive end. So I have a little partial positive, partial negative here. Now, between oxygen and sodium, you probably can guess which way this is going to go. But just to double check, oxygen is 3.5, and sodium is 0.9. So the difference between these two is 2.6. 2.6 is way over 2, so we know this is going to be ionic. One atom's going to retain total control of the electrons, and the other one's going to give them up. So, the sodium gives up the electrons. Sodium is a plus cation, and then the oxygen would have to be a minus charge. So if we rewrote this the way it should be, it's going to look something like this. We'd have to write a minus charge on the oxygen, and the sodium would have a plus charge, and then we call that an ionic bond. Okay, ionic bond right there. Now what if I change that a little bit? What if I gave you, instead of sodium methoxide, what if I give you methanol? Well, everything's the same, the X and the Y, it's going to be like A and B, but now I have an OH bond. So O would be 3.5, oxygen is 2.2, so the delta between these two is 1.3, that's going to be polar covalent. So this is going to be a molecule, not an ionic salt. This is a salt. This is a molecule. Okay, so they have very different properties when that's the case. Let's see what we got here. Okay, so polar covalent. Now there are exceptions, and that's why I put that 1.4 to 2.0. Let's take a look. Oh, so we would write this one as partial plus, partial minus, partial plus. Okay, we don't write full-on charges here. We just write partials. This is going to be real important because plus likes to be close to negative, and negative likes to be close to plus. And so parts of this molecule will attract other molecules nearby because of this charge. Okay. So let's take a look at an exception here. So up here I have magnesium bromide. So magnesium is 1.2. Bromine is 3.0. So the difference is 1.8. That's right in the middle. We don't know. The book I use would call this a polar covalent. But when we look at the temperature of the boiling point, 1250, this is not a covalent molecule. This is an ionic salt. Now, if we look at HF, H is 4.0, and H is 2.2, so the difference is 1.8. That's just like this one right here. But now look at the boiling point. It's 20 degrees. That's cooler than normal room temperature. Okay, so HF is clearly a molecule. Okay, it's not an ionic salt. So there's these exceptions, and that's why I spread out the range from 1.4 to 2.0. Okay, so that's the end of this particular section. I'll be doing another one on a later part of chapter 1. Okay.